Welcome back, guys. Today we are going to be looking at a very important result. Uh, if you solve a Cauchy-Euler differential equation by using the appropriate substitution y equal x to the power m, you'll be left with a polynomial equation. So you have to solve that polynomial equation to get the solution, and then you write the solution of the differential equation using the polynomial equation solution you obtain. So once you solve a Cauchy-Euler differential equation of order 2, you will have three cases because that will be a quadratic equation. The first case is when m1 and m2 are real and distinct. That means that the two values of m has real representation, meaning they are real numbers, and then they are distinct, they are not the same. You have y equals c1 x to the power m1 plus c2 x to the power m2, as we did in example number 2 or example number 1. So for example number 2, we are told that the repeated roots of a Cauchy-Euler differential equation for case 2 is if m1 and m2 are equal, meaning the two solutions or the two roots of the differential equation are equal, then y equals c1 x to the power m plus c2 x to the power m, the ln of x, is a general solution to that differential equation. And then for this example, we are told to derive this result. So to derive the result, we begin by looking at the general form of second order Cauchy-Euler differential equation. And we just go ahead and do it. That's ax squared y prime prime plus bxy prime plus cy equal to 0. In this case, we divide each term by the coefficient of y prime prime. So if we divide this term by ax squared, we'll be left with y prime prime plus divide this term by ax squared, we'll be left with b over ax times y prime plus c over ax squared times y equal to 0. Now, this is what we'll be left with. So in this case, the general form will be y prime prime plus p of x y prime plus q of x y equal to 0. So we replace this and this with some function of x, p of x and q of x. Now, when we are solving reduction of order in differential equation, there is a point where you have to use an equation if you are given one solution of the differential equation. So the solution will be called y1, and then the equation you are going to use is y is equals to y1, the integral of e raised to the power negative the integral of p of x dx, all divided by y1 all squared dx. This equation is very important. When you have one solution to a differential equation, you can use this equation to find the next solution, provided that the differential equation has two solutions and it is a second order differential equation. So in this case, x to the power of m, so x to the power of m is the first solution to the differential equation. We're going to find what will be the second solution. So we replace x to the power m in this expression. So we have y is equals to, so y1 is x to the power m, the integral of e raised to the power negative the integral of, what is our p of x? P of x in this case is b over ax, that's dx, all divided by y1 squared is x to the power m all squared, and then you have a dx right here. Okay, after that we move on to write y is equals to x to the power m, the integral of, want to integrate this. To integrate this, b over a is a constant, so it goes behind the integral sign, and then we just have e raised to the power of minus b over a, the integral of that's 1 over x dx, because when the entire thing goes out, you have 1, all divided by x to the power of 2m dx. So x to the power m all square is x to the power 2m. That's what we have. Now from here, we need to move on to integrate this. So we integrate this, we got the ln of x, so we got y is equals to x to the power m, the integral of e raised to the power of minus b over a, the ln of x, and then all divided by x to the power 2m dx. The integral of 1 over x dx is just the ln of x. Now after this, we have a very important step to take. So we are going to rewrite this. You are going to see what I'm going to do. I'm going to write this as x to the power m, the integral of, so this can be written as e to the power the ln of x all raised to the power of negative b over a. And then we're going to divide this entire result by x to the power 2m dx. So if you actually see what we did here, we brought this, because this is a product, so we brought this as the power of e, and then we raised everything to this power. According to the power of power rule, we multiply the two powers in that case. So what we have here is this. And then after we have done this, we can use the natural log properties here. E raised to the power of the ln of anything is just that thing. So you have y is equals to x to the m, the integral of e raised to the power, this is the same as x to the power negative b over a, all divided by x to the power of 2m dx. That's what we're going to have. Now, if we send this expression up, we have x to the power m, the integral of x to the power negative b over a times x to the power of negative 2m dx. This goes up, it becomes negative 2m. Now we want to derive a particular expression here that will be needful for the value of m. So this is what we will have, and then after having this, we have to know the value of m in terms of the quadratic equation we solve, which has double root, because we assume that the roots are double. So if you take this equation and assume this solution and replace the value of y prime prime and y prime as we did in example number 1, you have an equation like a m squared plus b minus a times m plus c equal to 0. That means that this is the equation we were actually solving. This is the equation we're actually solving to get the form y1 equal x to the power m. This is the equation we're solving. So now we have to solve this equation if the roots are repeated. In this case, m is the actual variable, so m is equals to minus b, and b is b minus a. Minus b plus or minus, using the quadratic equation formula, the square root of b squared is b minus a all squared minus 4ac all divided by 2a. But in this case, we assume that the roots are repeated. That means the discriminant is 0. So the discriminant is 0. This entire thing right here goes to 0. The entire thing goes to 0. And then we only have minus b minus a all over 2a. So this is the value of m for the repeated roots. This is the value. So move and replace the value here. We have y is equals to x to the power m, the integral of x to the power of negative b over a times x to the power. Now this is minus 2m. So we know m is this. So we say minus 2 multiplied by m is negative. So I'm going to use a bracket here. M is negative b minus a all divided by 2a. So what we observe here is that this 2 and this 2 cancel. Negative times negative is positive. That's dx here, and then this will be equals to x to the power m, the integral. So I say integrating, we have x to the power of negative b over a times x to the power of, that's b minus a over a. So what we can do here is to take one of the x, we have the x here. So we take one of the x and then we add the powers. So y is equals to x to the power of m, the integral. This is x to the power of, if we take these two, so I'm going to do the derivative of your negative b over a plus b minus a over a. So what you observe is that this and this is going to cancel out. This negative b and b is going to cancel out. You'll be left with negative a over a. And negative a over a is negative 1. So you have x to the power negative 1 dx. And if you can see, this is just the ln of x. So you have x to the power m, the integral of dx over x, which is x to the power m, the ln of x. Therefore, we have proven that if y is equal to x to the power m is one of the solutions of this differential equation, then y is equal to x to the power m, the ln of x, is a second solution. and that the general solution can be written as y is equal to c1 x to the power m plus c2 x to the power m the ln of x, which is this. So thank you very much for watching this video, and we hope to see you in the next episode of our epic classic videos.